Okay. Hello everybody, welcome to this first lecture on control engineering. So, what we will do is we will just keep it very short, a series of short lectures about 20-25 minutes each, sometimes even less. So, we will begin with a little introduction to systems and control, like what kind of tools you might eventually use in the course and some very basics or some very basic mathematical tools as well. Okay. So, let us start by defining what is a system. It could mean several things, but we will restrict what makes sense for us in the course. Right? So, by definition it could be a collection of some physical components, biological components, sometimes even abstract components which talk to each other to kind of perform an intended objective. From the control point of view, we can say that a system, when subject to a certain input, also called excitation, gives a certain output, right. We can also call it as the response of a system, and usually schematically we can draw it as a diagram like this. Systems could also be composed of several subsystems, and we will eventually see physical examples of this, right. So, like one system could be connected this way, S1 could be connected this way, or this S3 to S4 and so on, so that the overall input will give me some kind of an overall response of the system. Okay. So, what could be examples? Some of them are like very obvious. You take a case of a motor where I just give a electrical input and I just see the output as a mechanical energy in form of a torque. Air conditioner, the input again is electrical energy, output you can sense in the terms of heat energy, which changes the ambient temperature. Human body which is infected with a virus, the input could be the drug prescription which you take, and output could be the way the drug is distributed in the body, its effect on the body in killing the virus. We will see all this, how this could actually be modeled mathematically. And another not very surprising example is that of a car, where the input could be some kind of a signal which generates acceleration, and the output which you could obviously see is the vehicle displacement. Okay. So, before we start, so I will just introduce you to some notations in the course. The small letter t would denote the time variable. Input would usually be denoted by u of t, output would be y of t. If there is a certain delay in the time signal, we will denote that as delta. Disturbance would usually be denoted by w of t, which is a time varying disturbance, and f denotes any function, right, which maybe maps one variable to the other. Okay. So, how do we classify systems? Based on the nature of systems, we can have several varieties or several classifications, right. Some of them which we had already learnt in our signal systems course or our circuits course and so on. So, the first one could be something like a linear and nonlinear, static or dynamic, systems which vary with time, and systems which do not vary with time, as we call them as time invariant systems. And lastly, what we will deal with is causal or non-causal systems. Okay. So, what is a linear system? The system for which the output varies linearly with the input, right. And we all know that it just satisfies the principle of homogeneity and superposition. For example, a resistor, right. So, okay, let us see how this works. So, if I just take a resistor, right. So, why do I call it a linear system? Let us say first, let us see if we can define what is a linear function. If I say f of x, then a function is linear if f of x1 plus f of x2 is f x1 plus f x2. This is what we call as the superposition thing, the superposition property. And something called the homogeneity, if I just take f a times x, where a is just a constant, I just have a of x. Why do I call a resistor a linear resistor, a linear system? Essentially because, okay, so if I take R, I give it an input voltage V, the output I see is I equal to V over R, right. Now, what happens if I have two voltage sources, V1, V2, well, of course, with the appropriate sign conventions, and R, what is the current? So, the current I see here is, of course, V adds up like V1 plus V2 over R, which essentially is V1 over R, V2 over R, and this is the response which I1 which I would get only with voltage V1, and I2 the response which I would get only with V2, right. So, this is like I could just take the individual voltages, take the response and then combine them. How does homogeneity work? So, instead of V, if I say replace this by some constant A, some constant B, and I look at the current would just be A times V1, B times V2 over R, that simply would be again A V1 by R, B V2 by R, and so on. So, this is like again the response with voltage V1 scaled by a factor A added directly to the response or the current with the voltage V2 with a scaling B, right. So, this is an example of a linear system. We could also see, well, what if I have instead an inductor, say voltage is L di by dt, or in other words the current across an inductor follows this one V over L, right. Okay. So, what would happen if I have two voltage sources, right. So, my total voltage would be V1 plus V2 which goes across a resistor L, and that would generate some amount of current, let us call this I total here, dit by dt, right. So, what is this dit by dt? Okay. This dit by dt now can be written as V1 over L plus again V2 over L, in the same way as we did earlier for a resistance. This again should be what? The V1 over L is essentially, if I just take the response with just V1 as the source, similarly di V2 by L would be the response which I would take with only V2 as the source, and you say they add up, right, just define the superposition thing. And similarly even the homogeneity would follow, right. Okay. So, what does a nonlinear system do? Well, in a nonlinear system, well, the response does not vary linearly with the input, and of course, it does not satisfy homogeneity and superposition. For example, a diode. Okay, let us work this out as we did earlier for this thing. So, I was I0 e power v over tau minus 1. And you see, if I take again V as a combination of two sources V1 plus V2, I could never write I as some individual combination. So, now the total I would be E V1 plus V2 over tau minus 1, and this is not equal to I0 e power V1 by tau minus 1 plus I0 e power V2 over tau minus 1. So, the superposition does not hold, and similarly you can check with the homogeneity as well. So, if I just put a here, it will not be equal to A times I naught e power V over tau minus 1. That is just kind of straightforward to check. Okay. The other kind of classification is between static and dynamic systems. So, for a static system, at any time the output depends only on the current value of the input. Other words, they are also called memoryless systems, whereas for dynamic systems the output depends on the past as well as the present inputs, and these are systems which are called systems with a memory. Okay, what does it mean? Again, let us work out another example. Okay, so let us again take the example of V equal to IR, a linear resistor, right. So, if I apply a voltage V, it results in a certain current across my resistor, right. V is R and this is the output, and as soon as I say switch to V equal to 0, right, I just remove this guy, then what happens? Well, I instantaneously goes to 0, okay, which means the output is gone. So, the input is gone, the output automatically is gone, or it goes to 0. Now, take an example where I have a V, a R and an inductance. This is my R L, and if I write down the dynamics, it would simply be V equal to IR plus L di by dt, and I say I just put this voltage source, I let the system go on for a while, right, for a few seconds say, and later on what I do, I just take out the voltage, right, which means I am now looking at a circuit which looks like this, right. And I do this after some time. When I do this when I switch it off after some time, you would know that the inductance accumulates some flux or it stores some energy, or in other words, the initial current, when I just say I do this at t equal to 0 is not 0, there will be some current, and I write down the equations, it will be IR plus L di by dt is 0, and let me say I at 0 is some number I of 0. Then the current for all future times would be I of 0 e power minus of R over L times t. So, what you see is that as soon as V goes to 0, I follows a certain pattern, it does not go to 0 immediately. It will take some time to go to 0 depending on what the value of R and L are, and these are usually referred to as the time constants of the system. Okay. So, this is how we classify between what are called as static and dynamic systems, and the way the reason we say memory is that, well, they store some energy and remember something, right, and that they do not instantaneously go to 0, right. Mathematically it would mean that y of t is equal to u of t just at that time instant, like for example which we saw of the linear resistor. For the dynamic system, y of t would depend on u of t, its previous instances, what was, like if we talk in terms of the stored energy, it would just mathematically look something like this. If I want to say I at 1 second, it depends on all the previous instances starting from t equal to 0. For example, as we saw the inductor. Okay. Other examples could be the example of, or other classification would be in terms of systems which vary with time and systems which do not vary with time, as we call time invariant and time variant systems, and this should not be confused by the dynamics of the system. Like for example, if I in my earlier example here, I was varying with time, but this is also a time invariant system. We are not really interested in how I varies. So, what we mean by time invariant is the following, that the output of the system is independent of the time at which the input is applied. So, if I take the example of a resistance, I do an experiment say today for a certain V, I get a certain value of I, say V is 1 volt, R is 1 ohm, and my I obviously would be 1 ampere. So, if I do this experiment say tomorrow the same time, I should get the same reading, right, and those are systems which are time invariant, which means here we are concerned about the parameters of the system, the value of R, right. Okay. Now, what do the time varying systems do? Well, the output of the system depends on the time at which the input is applied. If I apply U, I get a certain response Y, and if I do the same experiment after a while, the response might change. Okay, how does the response change? What does it mean? It means, okay, take an example of the mass of an aircraft. As the aircraft moves, it keeps burning on fuel and its mass inherently reduces. So, if the mass at takeoff would be different than the mass at landing, which means the parameters of the system are actually varying. So, we are not classifying the time dependence in terms of the dynamics, but in terms of the system parameters, right. So, here the resistance would be the parameter, and in the case of the aircraft the mass would be the parameter. Okay. The last kind of classification which we would be interested in the course is that of causal versus non-causal, a very basic signal systems concept. A causal system is the one where the output is depending only on the inputs which are received either in the present or in the past. These are also called as non-anticipatory systems. Non-causal systems, they depend also on the future inputs, and the system anticipates the future inputs based on the past. For example, well, mathematically this would mean y of t will depend only on the inputs it received at t, it received at t minus 1 and all if at all any inputs at t minus 2 and so on. Well, a causal system could also do the reverse. It could also see what could happen at t plus 1 and get its outputs based on that. Well, basic causal systems, all systems we see around, most physical systems are causal in nature, a motor or a generator. It doesn't, my AC doesn't react to see what might happen tomorrow to give me an output today, right. Whereas, if I look at a weather forecasting system, I would look at what could happen tomorrow to kind of predict today. Or a more general example which we are used to. When I prepare for an exam, I prepare keeping in mind what could be the questions in the exam. These are non-causal systems. We keep in mind or we anticipate what could be the future inputs, or if I am playing a game or a cricket match, I decide what kind of pitch I am playing, what kind of bowlers the opponents would have, and then I prepare myself based on that. So, these are essentially non-causal systems. Okay. Now, what are the implications of this on control? Well, what is a simple control mechanism? Well, a simple control mechanism could be a mechanism which directs the input, takes it through other systems and regulates their output. Right? And a control system also alters the response of a plant or a system as desired. Typically, it could look something like this. Right? So, you have a plant which is to be controlled, could be a motor, could be a car, a missile or whatever. So, the controller gives it a certain control input, and then we want all this entire system, the plant plus the controller, to perform a desired objective. Right? I will say, well, I want to say set the speed of my car to a certain desired speed, and I could measure the speed. Right? So, this plant is controlled via a control input which the controller generates based on what is the desired reference. Okay. So, will this always work? Well, sometimes not. You have disturbances which are essentially unwanted signals which affect the output of the system. For example, people entering or leaving a room while an air conditioner is on, sometimes external environment. So, at morning 6 o'clock my external conditions would be different than what they would be at 12 or 6 in the evening, that could be modeled as a disturbance. And my controller should also be smart enough to eliminate the effects of these disturbances. Okay? And therefore, we need what is called as feedback in control. So, what does the feedback do? This feedback essentially, it senses the output, right. It gives a signal which can be compared to the reference. Say this is 24 degrees, if I talk of an air conditioner, this is 27 degrees. This guy will send the signal back to the desired reference and say, well, your output is not equal to the desired reference, and this difference will tell the controller to give a certain input which might set, or eventually from 27 degrees I could go to 24 degrees, right. So, the feedback senses the output of the plant and gives a signal which can be compared to the reference, and the controller action, the controller input is chosen or it changes based on the feedback. For example, the desired is 24 and the actual is 21 degrees. The controller action would be different when the output is 21 than it would be when the output is 27. So, the controller action changes based on the feedback, and feedback enables the control system in extracting the desired performance from the plant even in the presence of a disturbance. Say now this is 24 and I say, well, my temperature is also 24, everything is perfect, right. Then I say there is some disturbance, some 10 people enter the room or 10 people leave the room. Then if 10 people enter the room, then you would expect the temperature to go up to say 26, then this is being continuously monitored here, continuously being compared. Then this guy will say, oh, hold on, there is a difference in temperature, so the controller should perform an action to give a certain input to the plant to get back the 26 to 24, right. So, this feedback also helps in eliminating the disturbance, and we will see the exact analysis of how to eliminate the disturbance in the future lectures. Okay. What could be examples, right? We have been of course motivating ourselves with examples. So, a typical open loop air conditioner would look something like this, right. So, this room is the plant to be controlled, air conditioner is my controller, the control action could be on and off switch of the air conditioner, and I will have a temperature setting knob, right, or even as simple as a regulator on my fan. So, when I look at a control system, I should identify what is the process or the plant, in this case it is the room. What is the output? The output which I measure is the actual temperature of the room. What is the desired input? If I want a certain temperature, what could be the desired input over here? Are there any subsystems involved in the middle, and what is the actuator? So, we will slowly quantify or even model each of these and see what these mean in analysis and design of control systems. Okay. So, this was in the open loop case. Now, we could also, or all the air conditions, now we see are closed loop in nature, and we know that the air condition it helps us in maintaining a desired temperature. The plant in this case is my room, the control system or the controller is the air conditioner, the reference signal is a desired temperature which I want the room to go to. The control input could come as in terms of an on off switch. The output which I measure is the output temperature. Disturbance could be factors affecting the ambient temperature, like people entering or leaving the room, right. Okay. And then the feedback signal is the actual temperature is compared with the desired temperature to perform the on off control action. Other examples could be, well, when I am actually driving a car, I want to go from point A to point B, right. So, this is the desired, so I can fix a destination to say point B. Okay. Now, at each point I see how far I am from point B, and then I have a control system which is essentially my control action when I drive the car. The reference is the desired destination, control input is the steering mechanism which drives or steers my car from point A to point B, and the output which I measure or I compare myself to is the actual position. Disturbance could be several in terms of traffic conditions, road conditions, you hit a up slope or a down slope and so on, right. And this constitutes a closed loop control mechanism. Okay. So, what we have done so far? We have looked at classification of systems which would be important from the control point of view. We have looked at a very basic notion of feedback and its significance, right. So, what will we do in the coming lecture? So, we look at how to build models and significance of models, types of mathematical models, and what are the steps involved in modeling of systems. So, we will do that in the second lecture. Thank you.